Hi everyone, I'm Michael, and in this talk we're going to explore angles, trigonometry, so sine, cosine, tangent, and also triangles in this metric. So the first thing is, what is a metric? Basically, a metric is a way of defining distance. So we're all used to the Euclidean metric. An example that people are often given the idea of a metric is the taxicab metric. So if you can look here, the distance between A and B is not the same as going straight from A to B, but rather you got to go over and down because taxi cabs have to follow the roads. And so this is going to be similar to my metric. To be more precise, my metric will look something more like this, where distance between A and C there, the taxi cab will have to go over and down, and so that will be the distance between those 2 points. Distance between A and D will be over and over again, and then A and B will be down and over. So that's kind of the intuitive idea of looking or thinking about my metric. And so I'm going to talk about how, when we're getting 2 points, how we can figure out what the distance between them is. So first thing is we're going to change the axes a bit. So we're going to keep our x-axis as normal, but we're going to tilt the y-axis so that it's pi over 3 radians from the x-axis. And then we're going to implant on the axis a new axis called y prime. That's going to be pi over 3 radians from the negative x-axis. So you can see it right there. And so this is how we're going to use it. When we have 2 points and we want to find the distance between them, we're going to draw a line segment between those 2 points. We're going to draw a parallelogram around that line segment such that the line segment is the parallelogram's longer diagonal, and the parallelogram sides are parallel to the axes. So, and then the length between the 2 points will be half the perimeter of the parallelogram. So I'm going to go over some examples. So we have 2 points there. We draw a line segment between them, and then we want to draw a parallelogram around it. And so that's what it would look like. And so the distance between those 2 points will be half that perimeter. 2 points, line segment, and then draw a parallelogram. The sides are going to be parallel to the axes, and so the distance between those will be half the perimeter again. And 2 more, line segment, and then parallelogram. All right. So this is kind of a intuitive way of thinking about distance when we're given 2 points in this metric. And so since we're going to talk about angles and trigonometry, we need to know what the unit circle looks like, because that's how I'm going to define angles and trigonometric functions. So the unit circle is a collection of points that are all distance 1 from the origin. And so in this metric, the unit circle looks like a hexagon. So I included a picture of it right there. And so angles, what they're going to be is the measure of an angle will be, you take the angle and you place its vertex on the origin, and the arc of the unit circle, the iso length of the arc of the unit circle that it subtends will be the measure of the angle. So in my example up here, this angle measure here, it will be the length of this arc going around here. And so whenever the arc that the angle subtends, whenever it has a measure 1, I define that to be 1 m radian, and m radians, as we rotate them, they're not going to stay the same, except if they're integer value. So if it's 1, 2, 3, as we rotate those angles, they'll stay the same value, but if it's something like 0.4, 4.5, whatever, as we rotate them, the angle values will actually change. But there is a way to keep angle values the same. So since we use the hexagon or the unit circle to measure angles, the symmetries of the hexagon will be the symmetries of the angles. So that means that we can rotate, one thing is that the hexagon, you can reflect it across the x, y, or y prime axes, and it'll still look the same. So that means we can reflect angles across those axes, and those angles will have the same measure still. And we can also rotate it by pi over 3 radians or an integer multiple, because the unit circle, we can rotate it by pi over 3 radians or a multiple thereof, and it'll still look the same. So we can also, even if it's not an integer value, we can rotate angles by that amount. And so trigonometry. So just like in Euclidean metric, I'm gonna define sine and cosine by the unit circle, where sine is the y values of the unit circle as we go around. So we start at the point 1, 0, and we go around the unit circle. You can see the y value goes from 0 to 1, and it matches with this blue line I have up here. And if we continue this process all the way around the circle, we'll get something that looks like this. Now for cosine, we're going to use the x values. So starting again at 1, 0, going around the circle goes from 1 to 0, back, and then it'll go down to -1. And so we look at the red line, it starts at 1, down to -1. And then if you continue this process, it'll look something like this, and it'll repeat every 6. You can see here 6. So it'll repeat every 6 units. Next thing we're going to talk about is triangle congruence. This is congruence means that congruence means that two shapes share all the same sides and all the same angles in a particular order. So in Euclidean metric, we have rules angle, side, angle, angle, side, and side, angle, side. But in this metric, that does not imply congruence. So you can see here, these two triangles have the same angle, side, side, angle, side, angle, angle, side, angle, side, angle, and the same side, angle, side, angle, side. Okay, so side, angle, side, yeah. But you can see here that the longer length here is not the same. So these two triangles are not congruent. Side, side, side is also violated in this metric. You can see here that this triangle here has one length 1, 2, and 2, and clearly these two angles are different. But if we rotate it to the side and keep all the angles the same, or I'm sorry, keep all the side lengths the same, 1, 2, and 2, we can see that this is an isosceles triangle, and so isosceles triangles will have these two angles be the same value. And since this is just a reflection across the x-axis, we know the iso angles are also going to be the same value. And so we have two different triangles, even though all the side lengths are the same. The triangles are different, so side, side, side doesn't imply congruence. Angles add up to pi, or 3 radians in this metric. So if SS is violated, then the only congruence law left, it will be side, angle, side, because the three sides are already going to be congruent or the same, and the two angles will determine the third angle. Next thing is isotangent. So tangent is the ratio of sine over cosine, and so it's hard to tell here, but just like how sine and cosine are like piecewise functions, tangent is also a piecewise function. So you got like an asymptote kind of here, and then right here it's actually a different function. It's just a straight line, no curving or anything, and then back up to a asymptote curving line. And interesting enough, if you remember that sine and cosine, they had those points at certain places, and so that means that those points is not differentiable because it's a point. But oddly enough, tangent is continuously differentiable, except at the asymptotes, of course. But that's actually something kind of interesting. And also the derivatives. I also explored derivatives of tangent, cotangent, secant, cosecant, and actually the derivatives of tangent and cotangent are the same as in the Euclidean metric. So tangent's derivative in this metric is secant squared, and cotangent's derivative is negative cosecant squared. Yeah, I think I said that right. So that's some other things I have to look at, or been looking at, is angle sum. So I haven't found a simple formula for angle sum, and for those who aren't familiar with it, angle sum is just a way of, like, when you have cosine of or sine of two angles, you can deconstruct into individual cosines and sines of those individual angles. So I included the Euclidean angle sum right there for reference. And as I mentioned earlier, I'm also looking at to see if side angle side implies congruence. I haven't found a counterexample of that yet, but still working on it. Okay, so anyone have any questions?
Thank the speaker. Does anyone have any questions for Michael?
Could you go back to where you were talking about the parallelograms? I am not able to figure out what is it parallel to the axes?
Yes. So the parallelogram sides are going to be, well, two of them are going to be parallel to these axes. So.
Oh, one of the three. Okay, all right.
Yeah.
So in Euclidean geometry, we define an isosceles triangle to have a triangle with two equal sides, at least two congruent sides, right? And as a result, the two base angles are congruent. Now that doesn't happen in this particular one. How do you define an isosceles triangle? In this one?
Well, I didn't.
Or I guess how would one define it?
I'm thinking the same way as in Euclidean, like just two side lengths are the same, irrespective of the last one. So that would just mean that the angles, like being opposite, are equal. That rule doesn't apply in this metric. No more questions?
Say click again.
You had another question?
They already, but no.
Sorry,
We have track of the coordinates, it's x, y. We are ignoring y prime. Is there any particular reason why we chose y instead of y prime? Or leave out one and not have three of them? I don't know.
So basically we needed three axes because we're allowed to like move along these axes, and it's just a choice. The person who originally developed this metric chose to leave this as a coordinate, and then this y prime is just another axis hanging along. You could just you could make this the y, make that a coordinate, and then make this the y prime. It'll just affect what the formal definition of the metric is.
Yeah, I guess when you did the sign graph, you are using x, the x and the y.
Yeah.
Totally, and I was wondering if that would change if you start using the other y.
It would change.
And how it would change.
It would shift cosine, I think. It wouldn't shift. The sign wouldn't change, but I think the cosine would. But I didn't look into that really.
Thank you.
All right. The next session begins in about 16